And it's my great pleasure to introduce my friend Juho Joutsa. I've known him since 2003 when we started med school together in Turku. And after med school we both did our PhDs at the Turku Vet Center, and then we both did our postdocs in Boston. And he's going to talk about the studies that he did there.
Thank you, Lauri, and thanks for the kind invite to give this talk. And it has been really nice to visit your center. I'm really impressed of all the facilities and people working here. It looks like you have a good spirit and things are moving forward here. So the title of my talk today is Network-Based Localization of Brain Disorders. And like Lauri said, I started this work already in Boston, and I moved back to Finland in September to establish my own lab and further develop these methods and apply techniques. So the main idea of this work is to localize brain disorders. So I want to know where in the brain a particular disorder lives in. What are the causal changes that make these symptoms emerge in the patient? So like you all know, we have a huge amount of neuroimaging literature. There are so many studies comparing patients and controls, and this information is enormous at the moment, and we have learned so much about brain disorders by using these techniques. However, there are some limitations in these techniques. So it's difficult to define any causal relationships. When we compare patients and controls, there are many factors that influence on what we see in the brain scan. As in this, so like in this image, multiple blobs in the brain, some abnormal activity going on, but there's really no way to determine which are causal for the symptoms that patients have. We may do some sort of correlation analysis and so on, but still the actual causal origin may remain unclear. So how to determine causal relationships between brain malfunction and behavior? The traditional way is by studying brain lesions. When an acute lesion causes new onset symptoms, then there's a causal link between that brain lesion and the symptoms. Now, if all brain lesions that cause the same symptom into the same part of the brain, then damage in that part of the brain is likely to be causal for the symptoms. And we can use this information to localize normal brain functions that were disrupted by these lesions. So why don't we know where all the brain disorders come from? This is the clinical reality. So we have many symptoms, psychiatric, neurological, which lesions cause, but the lesions hit to the different parts of the brain. And there's very little common with these lesions or the locations where these lesions are, which leaves the question open, where do these symptoms come from? And this is where network thinking and connectivity comes into play. So by the development of modern imaging techniques, we now have multiple different ways to analyze connectivity. We can use ETI to analyze structural connectivity, resting state functional MRI for functional connectivity, EEG, and so on. And the technique that we have been focused on is resting state functional connectivity MRI. And for those who are not familiar with the method, in this method, the subjects lie in MRI scanner, and we scan their brains while they're doing nothing, just staying awake. And we measure the spontaneous fluctuation in both signal. And we can then take activity from one region and correlate it with the rest of the brain to find out which regions fluctuate on the same pace. And if some regions fluctuate in the same pace, or their activity fluctuates in the same pace, there's likely to be some sort of a functional connection between these regions. And this technique has been validated in animal experiments, showing that resting state functional connectivity MRI, evoked response patterns, anatomical connectivity, they give pretty much the same results. So, what I did in Boston, I was working with Associate Professor Mike Fox, who developed a technique termed lesion network mapping. So in this technique, we combine information from causal lesions with connectivity fMRI. And the technique proceeds in few steps. So first, we collect lesions that cause, let's say, Parkinsonism. And then we use these lesion locations as seeds for resting state connectivity fMRI analysis. The analysis is conducted in a large sample of healthy volunteers, in this case 1,000 healthy volunteers, and we think that this models the normal connections in the human brain. Similarly as, for example, structural MRI template, that's the normal structure of the human brain. With resting state functional MRI, we get functional, normal connector within the human brain. So in this technique, we take the lesion that caused certain set of symptoms and map its connections to the rest of the brain. We perform this same analysis for each of these lesions that cause the same symptoms. And we get a bunch of networks. When we then overlap these regions, we can find out if there are any common nodes, meaning that any regions that would be connected to all of these lesion locations. Does this sound clear? Okay, please feel free to interrupt me at any point if you have any questions. So, this is the foundation that we now build on, that we use as the basic method to identify the origins of brain disorders, and then work from there to develop new treatments for these disorders. I will show a couple of examples how the method has worked in neurological disorders, and try to provide you a proof of the evidence for use of this method. And then later in the talk, I will explain how we think this information could be translated to treatment. So, as proof of concept, I have focused on movement disorders. Why movement disorders? Because they have pretty objective findings. So tremor is quite easy to analyze compared to more complex psychological phenomena, for example. And these disorders usually have effective brain stimulation targets, so we can test how these stimulation targets relate to our findings. So first, Parkinsonism, which is the main symptom of Parkinson's disease, but you can find Parkinsonism in other conditions as well. Parkinsonism is a symptom complex: tremor, slowness of movement, and rigidity. And here's an illustrative case. This is one of the cases we used in our analysis. This is a 70-year-old man who all of a sudden developed left-sided hemiparkinsonism. And they did a brain MRI scan for the guy and found that there was a small lesion hitting directly to the substantia nigra on the contralateral side compared to the symptoms. And this makes sense since Parkinsonism, or at least Parkinson's disease, is thought to originate from the substantia nigra. Substantia nigra pathology is the hallmark of Parkinson's disease in postmortem evaluations. So we continued and collected all cases that we could find with stroke or other brain lesion-induced Parkinsonism. And this is the result. So as you can see, these lesions hit to different parts of the brain. There's very little overlap between these lesions, and not all of them hit even near to the nigrostriatal tract, which is considered critical for emergence of Parkinson's. We then applied lesion network mapping, so mapping the connectivity profile from each of these lesions and overlapping them, and found out that all of the lesions were connected to this small site next to the striatum. And this location matches to the claustrum, which was quite surprising to us. We did multiple different analyses to confirm the finding. We did some subsamples, defined Parkinsonism a bit differently, with only 2 out of 3 main symptoms, or with more strict criteria, the delay between the lesion and the emergence of the symptoms. And each time the claustrum popped out. We then compared these lesion connectivity profiles to random lesions that caused some other neurological or psychiatric symptoms, to other movement disorders, and the single region in the brain that was always specific for Parkinsonism lesions was the claustrum. And this is a quite new finding, so at first we didn't even believe this ourselves. But then when we started exploring the literature more closely, we found out that there's actually direct projections from the substantia nigra to the claustrum. There's connections from the claustrum to the striatum. There's connections from the claustrum to the motor cortical areas. So the claustrum is actually a hub in the motor system and connected to all relevant structures that have been implicated in Parkinson's. So in the end, I think it actually makes sense that we localized Parkinsonism here. And there's one recent study showing that there's severe dopamine and noradrenaline deletions in the claustrum in patients with Parkinson's disease. We then continued analysis to investigate whether this is specific only for lesion-induced Parkinsonism or whether it applies to all conditions that cause Parkinsonism. And we found atrophy maps from the literature. This is based on PPMI data, which is a huge Parkinson's disease imaging study, which is freely available, and they have a published atrophy map of Parkinson's disease. We then analyzed whether our lesion location connectivity predicted this atrophy pattern, and that was the case. And we repeated the same analysis with pseudoatrophy maps for progressive subnuclear palsy and multiple system atrophy, which both cause Parkinsonism. And again, our lesions showed more connectivity to these regions than some other lesions. So we think that this could be something common for all of these disorders and possibly the true origin of Parkinsonism in the brain. All right, then moving to cervical dystonia. So dystonia is a condition where people have abnormal muscle contractions, which can be very long-lasting and lead to abnormal postures. And cervical dystonia, so head and neck region dystonia, is the most common form of these disorders. It can be caused by brain lesions or can be idiopathic without any clear abnormalities in the brain. In worst case scenario, these can be really debilitating, and people are severely handicapped by the symptoms. In this figure is the current framework where people think that cervical dystonia localizes. So it's a corticothalamic cerebellar loop where there's consistently abnormalities in any kind of neuroimaging studies. And we again found that all the lesions that have caused cervical dystonia, which are shown here, and as you can see, again, they do not overlap. They may fit with these loops or regions shown in this figure to some extent, but for example, no cortical involvement whatsoever. We ran the lesion network mapping connectivity analysis and found out which regions connect all of these lesion locations. And what fits very nicely with the current framework is that we found that all of these lesions were connected to the cerebellum, to the midbrain area, to anterior thalamus, and negatively to the sensory cortex. No one knows exactly what negative connectivity means, but it's thought that it could be inhibitory connections. So losing inhibitory connections might release abnormally high activity in the sensory cortex, which fits that have been found in imaging studies, for example, in anatomical structural MRI studies. Cervical dystonia patients have abnormally large sensory cortex. They also have sensory tricks, so for example, if the head is in abnormal posture, they are unable to turn the head right. But if they touch their face, they can turn the head right. So this kind of fits that there is some sort of sensory processing abnormality in cervical dystonia. And when we compare these findings to all movement disorders and all other lesions, there are two regions that were specific only for cervical dystonia, were the sensory, primary sensory cortex and the cerebellum. Now to verify that this would truly be the origin of cervical dystonia independent of the etiology, so whether it's caused by brain lesions or idiopathic, we got access to a sample of cervical dystonia patients and controls. They have been scanned with resting state fMRI. So we used our regions that we identified to be specific for cervical dystonia lesions and analyzed their connectivity in this sample. So by definition, if we think that cervical dystonia caused by lesions is caused by these regions, and that's the origin of the symptoms, then these regions must be abnormally connected also in primary cervical dystonia. And in fact, we run like 50 different regions of interest, and these regions were the most abnormally connected of all of them, indicating that they are probably relevant for cervical dystonia. And we have continued along these lines and analyzed multiple different psychiatric and neurological symptoms. Most of these studies are still under review and published. We applied the technique, for example, this is probably interesting for you guys. So to depression, we had 5 different lesion data sets. In all of those cases, lesion had caused depression. There were multiple different definitions how they defined depression, but regardless of the definition and the data set, in each data set, all these lesions were connected to the left dorsolateral prefrontal cortex, which is also our TMS target in depression. We were hoping to find possibly new targets, but left DFC in this case was the only thing that was consistent across all 5 different data sets. We conducted similar analysis for migraine, and interestingly, the migraine lesions are connected to the insula, which has role in pain processing, and they were negatively connected to the visual cortex, which matches with the clinical symptoms in preceding the headache, like visual aura and so on. And the occipital cortex is actually the TMS target that has been approved by the FDA quite recently. Then we have applied the technique for more rare or even less well-known or conditions with even less well-known origin, and found out a couple of interesting findings. For example, stuttering lesions which seem to be connected to the amygdala and posterior parts of the putamen, suggesting that there are motor abnormalities and maybe something involved with emotion processing and so on. Any questions so far?
What's free will in the psychiatrist?
Yeah, excellent question. So we started by studying movement disorders. So we studied two different syndromes, alien limb syndrome and akinetic mutism. And in alien limb syndrome, one limb of the patient starts to live its own life, and the patient doesn't feel that it's part of him or her anymore. In akinetic mutism, the patient would be able to produce beats and move, but they cannot do it voluntarily. So we use these disorders as example of disordered free will. So the desire to do something, or the act of deciding to do something, or feeling responsibility for your own actions. So I'm a movement disorder guy, so I was mainly interested in these conditions, but we had a more psychiatrically oriented guy in the team, and he thought that this would also reflect some items of free will, and I think that's what got us to BNAS with this paper. All right, so then moving on. How is this relevant for treatment? Intuitively, I think that identifying the origin of a disorder tells us something where, for example, we should stimulate, which parts of the brain we should interfere with.
Sorry,
Yeah.
I just wanted to ask about the auditory hallucinations part too.
Yep.
So, were you involved in that study as well?
Yeah. So we found out all the reasons that cause hallucinations, and by far the most common two type of hallucinations are visual and auditory, and there's some overlap.
Are those like voices or any kind of?
So mainly voices, but any kind of auditory hallucinations. So we were expecting that these would connect to visual cortex, auditory cortex, but that was not the case. The lesions causing visual hallucinations are connected to lateral geniculate nucleus, and that's part of the visual system.
Mm-hmm.
So that fits. The lesions causing auditory hallucinations are connected to the cerebellum, and more specifically to the dentate nucleus, which is the output nucleus from the cerebellum. We don't know exactly how this causes auditory hallucinations, but this was specific for auditory hallucinations. So there's a clear difference between visual and auditory hallucinations.
Did you do a sub-analysis looking at voices versus other types of auditory hallucinations?
No, we weren't powered for that.
Because like in schizophrenia, it seems like people get voices, but other types of auditory hallucinations are much less common.
Right.
It would be interesting for schizophrenia research, for instance, if you could see voice more specific.
Yeah, good point. Yeah.
Do you remember what kind of hallucinations they have? Is it music or?
It wasn't music. It was really random. And so these are all like published case reports with the information that they provide. All right. So moving towards treatment. So first we started investigating whether this tells us something about treatment with Parkinsonism. So for Parkinson's disease, dopamine is highly efficacious medication. So almost all Parkinson's disease patients respond well to dopamine. However, in lesion-induced Parkinson's, only 50% of the patients respond to dopamine. So we analyzed whether the lesion connectivity, so whether it's a hit and whether it's connected to whether it predicted dopamine response. And dopamine acts in the acrostriatal system in Parkinson's disease, so glutamin is the main site of action for dopamine in this disorder. And our lesions that, or our cases with lesions that responded poorly to dopamine, they were more connected to the glutamin, indicating that their lesion may interfere the glutamin dopamine function more, and in those cases responded well to dopamine medication. We then continued this with deep brain stimulation data. So we had a sample of 100 Parkinson patients who all received subthalamic low-dose stimulation. And in each patient, the stimulation electrode, so the stimulation site, is slightly different. So we analyzed the connectivity from these stimulation sites to the claustrum that we identified with our methods. And sure enough, the stronger this connection was, the better the response for DBS in these patients. We then analyzed cervical dystonia data with a similar approach. In cervical dystonia, there's no good medication. People use botulinum toxin, but there's no really efficacious CNS medications. But DBS to the globus pallidus interna is highly efficacious in cervical dystonia patients. But again, not all patients respond to GPI DBS, but most of them do. So we have a collaborator from Germany, Martin Reich, and his colleagues, and they have defined, based on multiple different data sets around the world with GPI DBS, the ideal sites in the GPI or near the GPI that predicts best response. And we analyzed the connectivity profile of these sites. And sure enough, it matches quite well to what we find with lesion network mapping. So all lesions causing cervical dystonia are negatively connected to sensory cortex. The efficacious DBS sites are also connected negatively to S1. The lesions were positively connected to the cerebellum, and similarly, the efficacious DBS sites were positively connected to the cerebellum. So this indicates that the network that we identify may have some relevance for treatment efficacy. So the previous two slides I showed suggest that maybe hitting the network that we identify based on causal lesions may have therapeutic efficacy. However, in these conditions, DBS is usually contraindicated in cases where the symptoms are caused by a lesion. So the only condition, only movement disorder caused by lesions where it's okay to use DBS is Holmes tremor. Because this condition is always caused by lesions, it's perhaps the most severe form of tremor. People have resting tremor, action tremor, postural tremor, and they are often unable to perform any normal daily functions because of this severe tremor. So in these cases, we again collected all cases where lesion had caused Holmes tremor, and part of them had received DBS or neurosurgical lesion therapy. And in all cases where they responded favorably, the DBS or the neurosurgical target was connected to the lesion, indicating that they are part of the same connected circuit. In Holmström, there are recordings of brain activity after the causal lesion. So there's abnormal oscillatory activity which matches with the tremor frequency that I measure from the limbs. And when they use DBS, that disrupts the tremor, also this oscillatory activity goes away. So this suggests that the first lesion may set up some sort of abnormal activity oscillating in the system, and when you hit it the second time, that will improve the symptoms. So again, suggesting that the network that we find with this method may have some relevance for therapy. Any questions so far? All right. Then moving on, so we further investigated how we could use connectivity analysis to define treatment targets. So at the moment we have a handful of efficacious treatment targets for very specific conditions, and how those treatment targets have been identified is usually a matter of trial and error and serendipity. So there are also some rare cases where brain lesions can be beneficial for the patients. So in these rare cases, the patient had some type of movement disorder and then get a brain lesion which cures the movement disorder. In this case, essential tremor. And we investigated whether we could use these beneficial lesion locations and connectivity to define treatment targets. And as a proof of concept, with essential tremor, we found 11 lesions hitting, which hit different parts of the brain with very little in common, but when we analyzed the connectivity, all of these lesions were connected to a specific site in the thalamus, which matches exactly the coordinate that neurosurgeons used to target DBS for this condition. So this finding indicates that the connectivity actually can be used to identify treatment targets. If we would have lesions that improve some other brain disorder or whichever brain disorder, we could possibly use this technique to identify the treatment targets. The problem just is whether we have enough lesions improving some condition or not. And this is the first disorder where we have applied this methodology. So there are some reports of lesions disrupting smoking addiction, and we collected all of the cases that we could get from our collaborators and investigated lesions that disrupted smoking addiction versus patients who get lesions and continue smoking after the brain lesion. Remission of addiction in these cases was defined by that patients stopped smoking immediately on the same day that they got the brain lesion, and they reported that they had no difficulty in quitting. They felt no urge to smoke after the lesion again. And I think that these were evaluated at the time of the lesion, at 3 months and 6 months after the lesion. And we then defined the lesion networks and compared patients who remitted versus those who didn't quit. And this is the connectivity profile that separates these two groups. So lesions resulting in remitting smoking addiction are negatively connected to the medial orbitofrontal cortex. They're positively connected to the insula, DLPFC, and dorsal cingulate cortex. What was particularly interesting was the connectivity in the striatum. So the striatal findings do not survive correction for multiple comparisons, but there's a striking dissociation between ventral and dorsal striatum. So I think that what we think that these findings indicate, for example, for the striatum, is that these lesions that are positively connected to the dorsal striatum reduce its activity, but
Code White,
increase.
third floor diagnostics in the vicinity of room 3102, 3101. Code White diagnostics in the vicinity of room 3102, 3101.
Yeah, so what we think that happens there is that by disrupting the positive connectivity, the yellow regions, their activity goes down, and disrupting negative connectivity, so the blue regions, their activity goes up in these patients. And this might give us some sort of treatment targets, where to target, for example, brain stimulation.
Sorry, what did you say about the striatum? I lost, that it's differentially connected, and I thought you were...
Yeah, so the lesions that disrupt addiction are more positively connected to the dorsal striatum and more negatively connected to the ventral striatum. So the effects that these lesions have, or should have, is that they decrease dorsal striatum activity and increase ventral striatum activity. Okay, so now I've talked about how to localize different brain disorders and their possible relevance for treatment. So how to actually use this information, how to convert it to treatment. So as you know, we have different kinds of brain stimulation methods, and this could in principle be used for any brain disorder as long as we know where to stimulate. And neuroimaging, particularly PET imaging, offers us an opportunity to measure brain function during stimulation or after stimulation. So a combination of these techniques could be used to probe different targets and see whether we can achieve the desired change in brain activity. And for this purpose, probably the most useful method is TMS, since we can non-invasively change brain function, we can temporarily change brain function. So non-invasive methods are probably the first line which we should use to probe new targets before going into invasive.
Code White, all clear. Code White, all clear. Complet, complet.
So, to verify that whether our findings have actually relevance for the treatment or not, this is work that is currently in progress in Turku in Finland. So we take the Cervical Dystonia findings, we have patients who receive deep brain stimulation for Cervical Dystonia. Most of these patients respond well. We'll scan them with PET imaging, we turn the DBS on and off to see which part of the brain activate, deactivate, and how that affects their symptoms. And if our findings are correct, we should see activity changes in the sensory cortex and in the cerebellum that should correlate with the symptom improvement. And another project more directly testing the usefulness of our findings is, like I explained, to use TMS. We have easily available target in the sensory cortex, which we can modify with TMS. So we take the target that we identified, stimulate it with TMS, and again measure the effects using PET imaging to verify that we can actually change brain function towards more normal in these networks that we have identified. And hopefully that will lead to improvement in patients' symptoms. And finally, a step forward from these to generalize these methods to be applicable more broadly to brain disorders. We have tested whether connectivity-based TMS could be used to modify neurotransmitter function specifically in some networks while avoiding other networks. So we took some regions that represent different network areas in the striatum, used these as seeds for resting set connectivity analysis, defined which prefrontal cortex regions are most connected to these sites. And same with the red regions in the striatum. We then applied intermittent theta burst to these targets and measured changes in dopamine function using PET imaging. And sure enough, this is just based on our first case, so we are still collecting data. But in this case, it looks really promising. So after stimulation to the blue side, we predicted that we would see dopamine response in these blue regions, and that's exactly the case. Same with after stimulation to the red target, which is connected to the striatal red targets, we saw dopamine release in those regions. So if these findings hold true, then this technique could be used to specifically modulate dopamine function in one network while avoiding others. That could be useful, for example, for Parkinson's disease. They have motor symptoms that are due to the low dopamine function in motor system, but at the same time they may have too high dopamine function in associated striatal regions or in the ventral striatum, leading to, for example, psychotic symptoms, impulse control disorders, and so on. Similarly, for example, schizophrenia, when you treat the positive symptoms with antipsychotics, you often get Parkinsonism or motor symptoms due to blocking of dopamine function in the motor circuits. So this could be a potential method how to specifically treat one type of symptoms without affecting the other or blocking some unwanted side effects. And this is also something that we'll continue collaborating with Laurian and Sarah also here in Oklahoma. Right. My time is almost up. So in summary, the work that we have done and the main aim we have is use lesions and connectivity to define where neurological and psychiatric symptoms come from, what is the causal origin of these disorders. We then aim to confirm the findings in a sample of patients with similar symptoms with unknown etiology, then find if there's anything that suggests that this may have relevance for treatment, and finally use these findings to target brain stimulation and test whether we can actually change the brain back towards more normal and alleviate the symptoms. And if all of these steps go true in a disorder, then I think that the brain stimulation treatment would be ready for a pilot trial or RCT soon. So that's the main aim, and in principle you could use this technique for any brain disorder you like, as long as there are enough lesions that cause this symptom. Right. Do I still have time, or what is the?
10 minutes.
Okay, very good. So, just to finish with some thoughts and more provoking findings. So as you know, that there has been a lot of discussion of reproducibility crisis in
Your
neuroimaging.
attention please, the coffee shop at the main entrance is now open. Votre attention s'il vous plaît, le café de bénévole à l'entrée principale est maintenant wide.
The findings
Coffee
in
shop is now open.
between studies do not replicate very well, and different studies find abnormalities in different regions. And this has been suggested to be caused mainly by too small sample sizes, inadequate correction for false positives, but another explanation could be that these findings are more of network effects and just localized to any single brain region. And I'll give you an example of Alzheimer's disease. So there's a huge amount of studies in Alzheimer's. For example, structural MRI studies, there's tens or even hundreds of studies comparing Alzheimer's patients to healthy volunteers. If we take all of these coordinates, all the findings in these structural MRI studies, and run them through daily meta-analysis, that is meant to find whether there are any common regions with stringent statistical thresholds. With structural MRI, there's only atrophy in the hippocampus is something that is consistent through almost all the studies. When we look at glucose metabolism PET imaging, there's just some tiny clusters here and there, but nothing in the hippocampal area. When we repeat the analysis in SPECT imaging, there's again some regions pop up, but they do not match the MRI or SPECT findings. So it's difficult to say which regions are the most important and why this is the case, why we see so different findings and so little findings in all of these studies. So, as we did with brain lesions, now we use the atrophy coordinates as seeds for the analysis. And with the hypothesis that the heterogeneous neuroimaging findings could be explained by the fact that they are part of the same network, but just different modalities have different sensitivity for different parts of the brain. So when we run all of these coordinates that we extracted from all of these studies through the connectivity pipeline, the results start to look much more similar across different modalities. So this could be an alternative interpretation for the crisis of not being able to reproduce findings in neuroimaging, but of course needs further validation. Right. Thank you for your attention, and if you have any questions, I'll be happy to answer.
That was great. I think we've got hours of questions. But I just want to, especially with the Parkinson one, we started with identifying the structural lesions, then identified in the claustrum these functional connectivity locations. Have you ever gone back to the people, your patients, and checked that region, the claustrum, to see the health of that region? You didn't have a lesion in the first place, but there's something now that you know it's important that you can go back and see if there's something special there.
Yeah, that's an excellent question. So we didn't have access to these patients ourselves, so we just had an image of the lesion or the scan. And claustrum is such a small region that it's really hard to investigate with any neuroimaging modality, and I think that's why it has been largely ignored. It's really close to putamen, for example, which is severely affected in Parkinson's, so it's difficult to investigate. And yeah, so we unfortunately didn't have access to these patients, so they are like post-mortem examinations. But in general, in Parkinson's, in post-mortem examinations, there is a severe damage in the claustrum.
Or maybe going forward more in newer Parkinson's studies, or with newer patients, look at that brain region.
Yeah, absolutely.
functional connectivity can be disrupted a variety of ways. The C regions, it could be targeted or connected regions, and it could be the connectedness between them. So it just made me think if, I guess similar to what you sort of mentioned, but if you've been able to understand this probe more structural connections, more structural changes in the brain that might explain the pattern of functional connectivity that you observe. A lot of it makes sense, and some of it is actually pretty surprising. So it would be interesting to see, for example, say like white matter connectivity, or reduced gray matter density or density, that sort of thing.
Yeah.
Have the opportunity to do that.
Yeah, that's excellent point. So we are currently in progress of doing that. So if our hypotheses are correct, we should be able to predict that atrophy, for example. So we are now in the process of analyzing repeat scans from patients who get acute brain lesions, and with the idea that based on the lesion connections, we should see more atrophy in the connected regions. But this work is still in progress. But
Yeah, particularly for the Parkinson's findings, that tract, it makes a lot of sense anatomically.
yeah.
In the area that you identified, there's a lot of fiber crossings, and so it's a difficult region to assess with white matter analysis, but it's, the techniques are moving in that direction, so there can be a lot of interesting possibilities there, I can imagine.
Yeah, absolutely. And some groups are using tractography-based analysis in a similar way that we are doing. It has many advantages over functional connectivity, but also disadvantages. I think that the main disadvantage is that it's not really good on assessing polysynaptic connections. So if there's one track and that's disrupted, that's easy to identify and everything should map to that one track. But if there are some brain matter regions in between, then it's hard to make these polysynaptic connections.
Could you talk about the balance of confidence that you have in these findings depending on the disorder and the source? In some cases, you have access to a huge data set, and like PPMI or ADNI or whatever, everybody can look at it and can verify what you found before. In other cases, though, it sounds like you scoured the literature and got in touch with colleagues who might have relevant data, but in the smoking remission, for example, after a lesion, I think was that looking at the literature, or other cases were looking at the literature, to worry about missing cases that just ended up in a file drawer, where, we didn't have this cool result, we're not writing it up, but team B, they did have this cool result, they had this patient who stopped smoking, and that's why it ends up in whatever journal. So is that a challenge for some of these projects, some of these data sets?
Yeah, that's an excellent point. So I think that it's a challenge for all of our projects. So people are, for example, with case reports, people are likely to publish the ones that make sense.
Yeah.
And if they don't, they may not be able to link the lesion to the shopping centers. So yes, that's definitely a challenge. The reason why we are still confident with our findings is that we have always identified regions that are connected to all of the lesions, or almost more than 90% of the lesions. But you're right that there could be some bias. Still, that's possible.
Do you think that access to the data at the Turku University Hospital could alleviate some of those fears? Have a more systematic.
Yeah, absolutely.
Could you mention what your plans are?
So in Turku at the moment we are collecting more lesions. So we have only had access to a handful of disorders so far. So now we are planning to collect retrospective data and also prospective data. But the challenges with these are that with these approaches, especially with the retrospective data, we are limited to symptoms that are recorded by neurologists. So, for example, psychiatric symptoms are often not that well recorded after brain lesions. People may not be able to link the two. And with prospective data, the challenge is that we are likely to end up with very limited number of rare cases, but common cases we have better access to. So currently we are working with, for example, epilepsy, which is quite often caused by lesions. So that's an easy target for us. But it depends on the condition. How
It's actually a question that I have. Depends on the etiology. Have you seen any difference in your research? Because there's epilepsy, there's inflammatory, there's vascular. So the term lesion itself, have you seen any differences?
Yeah. So the main difference is that ischemic strokes work the best. It's really clear if you get one vessel is occluded and there's an infarction behind that vessel. But for example, infiltrative tumors, the results are much more noisy.
Yes. And another question: do you have any experience in MS, multiple sclerosis? Because there's a variety of symptoms and also a variety of lesions. And the lesions are very anatomically located in specific ways in order to make a diagnosis.
Yeah, so I think that one application of our methodology could be MS. So to predict which MS lesions cause the symptoms, that would be possible. The reason we actually haven't included any MS patients in our analysis, just because of the fact that they often have multiple lesions, and we don't know which one of those is the causal lesion.
There are many symptoms.
Yeah, exactly. But maybe we could, if we would define the networks based on strokes, we would then apply the findings to MS and figure out which are the causal lesions. But using MS as the starting point doesn't work that well.
I wonder, do we still have time? Are we going to be keep time?
I'll check the hallway. There's supposed to be another group coming in.
Okay, just go on. I'll hold on.
I was wondering, is that a challenge for Parkinson's or Alzheimer's, where you have these complex syndromes? It's usually not just one symptom in these patients. So how is that addressed?
Yeah. So, for example, in our study, we focused on Parkinsonism.
Yeah.
So it's the motor symptom that they have. For example, Parkinson's, they have lots and lots of other symptoms. So we don't know where those come from. We just know where the core motor symptoms come from.
And in case of Alzheimer's, the data that you showed?
So I haven't been working with Alzheimer's, but I know that Mike Fox at Harvard is
Dr. Paternity.
focusing on lesions that cause episodic memory impairment. But I don't know about the results. Sorry.
It's interesting to see how there's often, you find nearby parts of the brain that are differently connected to the lesion in one place. It's inhibitory action, blue and orange or whatever. But I wondered how, if you're going to talk about using neurostimulation to target these things, it might be hard if those things are close by each other to be specific. It's not very specific at a time.
Yeah, that's definitely a challenge. It's easy for larger cortical regions, obviously. But in some cases, we may not always have to be precise and stimulate only that one spot. It could be enough that if we just blast that area where the original is. But it depends on the condition, and we know after we have tried.
Yeah, I was involved in this study, where they're using TMS to target the insula for smoking cessation.
Yeah.
Schizophrenia. So I was, just looking at that image you showed, made me wonder if, because I thought there was like a medial prefrontal cortex, that's blue, and whatever it generates in orange. I wonder if we're specific enough to get one and not the other area. That could impair.
Yeah, I guess the the study you're referring to used the H coil, like the
Yes.
I think that it fits relatively well to our findings. Like it should reach insula, it should stimulate everything like in the dorsal part of the frontal cortex, and the effect is at least much lower in the medial
Yeah, it's
prefrontal
too
cortex.
deep, I guess.
Yeah, exactly. So in that sense, it probably fits.
Any more questions? Let's thank you all.